So by this point, we've seen a few times that pattern I've mentioned in terms of taking complements of quantities with set algebra, and we're going to very specifically define it and show a little bit of how you can prove that it works in a more general sense, where we have what's called De Morgan's laws, or De Morgan's rules if you prefer. Basically what they say is that if we want to take the complement of a union, that becomes an intersection of complements, and if we want to take a complement of an intersection, that becomes a union of complements, because the intersections and unions are kind of, but not quite, opposites. That is, if we have A union B quantity complement, that becomes A complement intersect B complement, while A intersect B quantity complement becomes A complement union B complement, as we've seen before, but let's actually be sure this time and show that that works. So for this, we want to use the given diagram to show that A union B complement is equal to A complement intersect B complement. And the way we do this is in terms of those generally defined regions. So that allows us to say this works for anything at all as long as we get the right regions on either side. So here, let's talk about what A and B are. That we have A is the regions, in this case, 1 and 2, while B is going to be the regions 2 and 3. And as a result, when we take these groupings, if we talk about their union, A union B, this, by default, must end up being 1, 2, and 3, because it's either. Sure. Which tells us that if we took the complement, A union B and everything else, is just going to be that remaining region 4. Okay, so with that general picture, we know that A union B quantity complement is the stuff outside the bubbles, but here we have a specific notation for saying what it is. It's the region numbered 4. On the other hand, if we talk about the complements first, we will have that A complement is going to end up being 3, along with 4, while B is going to end up being, well, 1 and 4. Or excuse me, not B, B complement, very importantly. So if we took A complement and intersected that with B complement, we'd want to define the things that are shared to both of these, which, again, is 4. So we have the desired result. And this is only one part of De Morgan's law. If you want to show the other one, it'd work very much the same way with very much the same logic. But instead of doing that, I'm going to do one that's a little bit more complicated, but that we've also seen, at least hinted at, before. So for the given diagram, we want to show that A union B intersect A union C is equal to A union B intersect C. So for this, we're going to follow through on the same sort of logic, except with more pieces. That when we take A, we have 1, 2, 4, and 5. B will be 2, 3, 5, and 6. And C will be 4, 5, 6, and 7. So if we talk about those unions, A union B is going to end up being 1, 2, 4, 5, and 6, while A union C is 1, 2, 4, 5, 6, and 7. So if we end up intersecting those two unions, we would get 1, 2, 4, 5, and 6. Meanwhile, if we take B intersect C, that's just going to be that shared region in the middle, which is 5 and 6. Take the union of that with A, we will get 1, 2, 4, 5, 6, just like we expected, just like we did before. So that idea of distribution does work. And if we did something with intersections where we flop those signs, it would also still work for, again, very similar reasons. But I'm going to leave that to you guys to think about. I'm going to leave that to something that might be in the homework to think about, where this is it for our first unit. This is it for our second chapter. We're going to be moving on to chapter 3 next, but before we get into that, you got a small thing to worry about called an exam. I know some people take those very seriously, so you want to focus on that for now. But anyway, that's all we got for our first unit. Good luck on the exams, and I will see you in chapter 3 when we get there.